أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. In today's lecture we will be discussing the number systems. This lecture has been taken from the course outline of Introductory Electronics. We have almost finished the analog part of the electronics and now we are moving towards the digital part. So this is actually the first lecture from the digital electronics. So in today's lecture we will basically try to understand the number system. We will move toward the different number systems and then we will discuss the number system mathematics, and at the end of the lecture we will discuss the conversion of different number systems with each other. So let's come toward the general number system, that what we are talking about, that is actually base 10. So we are normally familiar with the decimal number systems that is considered that is called as a base 10 number systems. So except this number system we have some other number systems that are binary number system which have base 2. We have octal number system that have base 8, and another number system is hexadecimal number system that have the base 16. So we need to discuss each of the number system in detail. So in total we have 4 number system. The first one is the decimal number system that have the base 10. The second one is the binary number system that have base 2. The third one is the octal number system that have the base 8. And finally the last one is the hexadecimal number system that have the base 16. So what are the major characteristics of numbering systems and why it is so important to us? So if we look towards the different number systems, in some the digits are consecutive. So the numbers of digits is equal to the size of that particular base. Just like for binary number system, the base of that is 2, and for the octal number systems the base of that is 8. So definitely there will be 8 digits in these systems. So if we are looking towards the decimal number system, so it will have 10 digits, and in the case of hexadecimal number system, as it has the base 16, so it will have 16 digits. So 0 is always the first digit in all the number systems, even if it is binary, octal, decimal or hexadecimal. So the base number is never a digit. So when 1 is added to the largest digit, a sum of 0 and a carry of 1 results. So in different number system we have different arithmetics, just like the addition, subtraction, multiplications. So now there are some rules for that. So when 1 is added to the largest digit, a sum of 0 and a carry of 1 is resulted. So numeric values are determined by the implicit positional values of the digits. So this is what we will learn from the number system mathematics. So let's come toward the significant digits in different number systems. So first we try to understand the significant digits in case of binary number system. We have a simple number like this. This is something from the binary number systems. We have most significant digit, that is this one, and we have least significant digit, that is this one. So this is in case of binary number systems. If you want to know the most significant digit and the least significant digit in the case of hexadecimal number systems, then here in this example 1 is the most significant digit in hexadecimal number system in this particular numbers, and a is the least significant digit in case of this particular hexadecimal values. So first we would like to discuss each of the number system in detail. So starting from the binary number system and then moving toward the octal, decimal, and finally ending at the hexadecimal number system, we will try to elaborate each of this number system individually in detail. So let's come first towards the binary number systems. So that is actually called as a base 2 number system because the base for this particular number system is 2. So the binary number system is used to model the series of electrical signals in computers, and that uses that is used the digital systems to represent informations. So that is actually the computer coded language. So in this particular case we have two digits because it's a binary number systems. So we have 1 that is considered to be no voltage, or that is considered to be the off state of that particular systems, and we have 0 represent the no voltage or an off state of that particular systems, and 1 represent the presence of voltage or an on state of that particular systems. So the whole binary number systems runs with 0 and 1. 0 represent the off state while 1 represent the on state. In case of 0 there is no voltage moving through the circuit, while in case of 1 the voltage is there and that is moving through the circuit. Now that is applied to the circuit. So this is the binary numbering scale. If we look towards, we have this is base 2 number systems, this is base 10, this is binary, this is base 10, and this is the power of that, and this is the position values. So if we have 0 0 0, we can write in base 10 that is equal to 0, 2 power 0, and that is equal to 1. Similarly for 0 0 1 it's equal to 1, and its value will be this one. And just like in this conversion, we can have this simple table where we can convert the values. So we have some conversion, that how we can convert the decimal number system to binary number systems. So the easiest way to convert a decimal number system to its binary equivalent is to use the division algorithm for this particular case. This means that we need to use the division algorithm to convert the decimal number system into binary number systems. So this method repeatedly divides a decimal number by 2 and record the quotient and remainder. So in this particular case, the remainder digits, that is actually a sequence of zeros and ones, forms the binary equivalent in least significant to most significant digits. So we can move through from the least significant digit toward the most significant digit, and that will form the binary value or the binary equivalent of that particular decimal values. We have a very simple case where we have 67, that is actually in the decimal number system, and we would like to convert that into binary number systems. So all the division algorithm is clarified here, and all the steps are very clear and simple in this particular case. So let's come to the first step, where the objective of this slide is to understand how to convert 67, that is actually in base 10. Base 10 means decimal number system, toward the binary equivalent. Binary means base 2 number systems. So the first step is that we need to divide this 67 by 2. So what happened if we divide 67 by 2, it will result 33. 33 into 2 is 66, but there is one remainder. So again we do the next steps. In the next step we need to divide 32 divided by 2. So what happened, we have a remainder of a 1, and there is again 1, and because 16 will comes, because 16 is the 32. So what we do, we repeat the same process again. So 16 can be equally divided by 8, and that will result into 0 remainder. So in the next step we need to divide the 8 by 2, so that will result 4 and the remainder is 0. And in the fifth step we need to divide the 4 again by 2, and that will gives us 2 and the remainder is 0. And finally we need to divide 2 by 2, that will gives us 1 and the remainder is 0. So again 1 by 2 is 0 and the remainder is 1. So we can divide that into 1 0 4 0 1 1 2 in the base 10. So this is actually the we need to stop when quotient equal to 0, I mean when the value become equal to 0. So in this way we have converted the 67 into 1000011 into 2, that is the possible. So this is actually the binary equivalent of 67, that is in decimal number systems. So how we can convert the binary into decimal number systems? This seems to be different things. In the last slide we have done how we convert the decimal into binary. In this slide we want to know the conversion from binary to decimal. So the easiest method for converting a binary number to its decimal equivalent is to use the multiplication algorithm. So multiply the binary digit by increasing power of 2, and we need to start from the right. So then to find the decimal number equivalent, and then we need to sum the products, and that can give us the decimal values or the decimal number systems values. So we need to divide a value that is 10101101 at the base 2 into its decimal equivalent. So what you need to do, we need to start from this side, and starting from 2 power 0 multiplied by 2 power 1, 2 power 0, from this side 2 power 1 and this side 2 power 7, and that is 1 to 8 3 32 plus 8 plus 4 1. And then finally if we add up the product, so it will give us the 173 in the base 10. So in this simplest way we have converted the value from the binary number system towards the decimal number systems. So this is how we are playing with the number conversions. So in this two slide we understood how we can convert a value or a number from the decimal into binary, and then similarly from the binary into decimal. So let's come toward the octal number system that has the base 10. In the octal number system we have digits, but the digits starting from 0 that ends at 7. So in total we have 8 digits in this particular number system, and that can readily convert it to binary number systems. So what we do in this, we have group of 3 binary digits can be used to represent each octal digit, and then we also need to use multiplication and division algorithm for conversion conversion to and from base 10. So it means in the same way we can convert the octal to binary and then binary to decimal, and that is a very easy way. So we have another number system that is the hexadecimal number system, and in the hexadecimal number systems we use the digits that is from 0 to 9, and then we have some letters that is A, B, C, D, E, F, and the group of 4 bits represent each of base 16 digits. So if we look toward this table in this hexadecimal values, the binary equivalent for the 10 is A, for 11 is B, for 12 is C, for 13 is D, and for 14 is E, and for 15 is F. So that is the hexadecimal equivalent of the decimal number systems when we convert a value from the decimal number system into hexadecimal number systems. So this is what we are going to discuss, the hexadecimal number system, which is also an important number systems. So we have some conversion factor, and we need to know in this slide how we can convert the decimal to hexadecimal. I mean, if a value is given to us in the decimal and we need to convert that into hexadecimal, so what will be the particular step for that? So let's come to a very simple example. We have a value of 830 that is in the base 10 in the decimal number system, and we need to convert into its hexadecimal equivalent. So we need to divide that by the base. The base for this particular case is 16. So it will be, if we divide 830 by 16, it will have the value of 51, and the remainder is 14. Similarly, if we divide 53 by 16, it will have the value of 3, and the remainder is 3. And similarly, if we divide 3 by 16, it will have the value of 0, and the remainder is 3. So the value will be like 0, 3, 3 and 14. 14 is actually equal to E, and that is the value of the base 10 of this particular hexadecimal number system. So in this way we have converted a simple value from the decimal number system into hexadecimal number system. So that is actually the simplest way how we can convert the value from the decimal number system into hexadecimal number systems. We have again, this was what we had done in this slide, from decimal to hexadecimal. What step we need to follow if we convert hexadecimal value to decimal number systems? So for this case, what step we need to follow to do this simple conversion? I mean, convert some value from the hexadecimal number system to decimal number systems. We have a simple value that is 3B4F16 to its decimal equivalent. So we have hex digits for this particular case, that is 3B4F. So we need to multiply by the base 16 in this particular case, and in this case we have this is a simple case where we have 16 power 10 multiplied by plus 16 power 1, 16 power 2, 16 power 3, and if we add up this value, the value what we are getting from this from after the product, we need to do the summation, and from this summation we can get the value who's 12,288 plus 2,816 plus 64 plus 15, and that will gives us the value of 15,183, and that is of the base 10. So we have the value that is achieved or that is obtained here, and that is of the base 10. So what we are moving toward the next steps or the next conversion, and that is actually the conversion between the binary to hexadecimal number systems. I mean, how if a value is given to us in the binary, how we can convert that into hexadecimal number system. So for this particular case, we have the easiest method for converting binary to hexadecimal is to use a substitution code. So each hexa number converts to 4 binary digits. So we have a simple case, and that is the substitution code for here. Just like 4 times 0 is equal to 0, or 4 times like this. We have a substitutional code that is mentioned in this table, and each of the digit in the hexadecimal that has the binary equivalent. Like for the 0 in the hexadecimal, that is the binary equivalent of 4 times 0. for the 1 in the hexadecimal, binary equivalent is 3 times 0 into 1, and similarly if we come toward the AND, that is the F. So in case of F, the binary equivalent is 4 times 1. So in this way what we do the multiplication. So we have some review for this discussion, and that is provided that how we can convert the number that is in some particular number system, and then we need to convert that into other number system, just like value is given to us in the digits, and we need to convert into its particular counterpart, whether it's a decimal, hexadecimal or octal number system. So in case of base 10, we need to use the power of 10, and then we need to do the simple mathematics to find the value. We have the same steps that we already done in the earlier slide, but anyhow that is a some sort of repetition, how we can convert the binary into decimal. So we can use the trick to convert the binary into decimal, and for this case we need to use the base 2, and just like we have a simple example like 1101.01 in binary, how it will be equivalent to its decimal counterpart, decimal values. So we need to do a simple method, that is the values beyond the point is has the minus powers. So just like 2 power minus 2, 2 power minus 1, and then 2 power 0, 2 power 1, 2.2 and 2.2 power through, and then we can simply add up that values, and then we can from this addition we can get the decimal number values. So that is a simple method how we can convert the value from the binary number system toward the decimal number systems. And this step is here, and that is clarified, that is decimal counterpart will be equal to like 0 0 this one, and then the decimal counterpart is 13.25. so when we converted this value from binary to decimal, it will have this value. So how we can convert the decimal to binary? That is we need to use the value concept of remainder, and that is just like 162 point this one, and then multiply. If we have point, we need to multiply by 2 as well, so that it become 1, and then finally we can add up, we can combine the remainder and then finally get the values. So in this particular case, when we divide 162 by 2, so we have remainder of 0, and the value is 81 we need to divide by 40. In case of 40, it will have one remainder and 1 0 and 1, and then 20 10 5 2 1 0, and then finally we add up, we just move from that, and then we can find the value in the binary equivalent. So we have base 16, that is actually the octal hexadecimal number system, and we can also convert the value from the hexadecimal into hexadecimal number system to binary number system, and similarly from binary number system to hexadecimal number system. The hexa value could be converted into decimal number system, into octal number systems, and in the same way the octal and hexadecimal value could be easily converted into hexadecimal and binary number systems. So this is some technique what we are doing, or what we are playing with, to calculate the decimal or the hexadecimal counterpart of that. So binary and hexadecimal conversion is very easy. We have a hexadecimal value, that is 261.35 in the base of 16, and we need to convert into decimal number systems. So what we need to do, we need to do this the base 16. So convert from binary to hexa. So we need to make groups of 4 bits starting from the binary point and add ones to the ends of the numbers if needed. Then just convert each bit group to its respective hexadecimal values. So we will have this just like 4 digits: 1011, 0100, and 0010, and then 1100 in the base 2. And then finally we can convert each of the digit each of the 4 digit values, so that is the B42C. So that has the value that is converted from the binary number system into octal number, into hexadecimal number systems. So in the same way we can easily convert the value from 1 till for 14 in the numbers 14 in the hexadecimal number system into binary number system. So that is the equivalent of that. So we have 2 complement, that is the binary number system can be represented using sign and magnitude. If n bits are used to represent the number, then the last bit is used to hold the sign of the number, while the other n-1 bits are used to represent the values. So 0 is used for negative sign and 1 is used for positive sign. That is what we do in digital electronics. So to get the 2 complements for any number, follow the following 2 steps. What you need to do, the first step is convert each bit in the value into its complement, that is 1 to 0 and vice versa, and similarly add 1 to the right side of the each step, and then finally move towards the value. So we have binary addition and subtraction as well. In the case of binary arithmetics or binary addition and subtraction, if we have a number that is positive, keep it its sign and magnitude form, otherwise represent the number that is the magnitude only and its 2 complement. So what we need to do, we need to add the binary numbers in the ordinary way is the decimal number. So the addition in decimal max carry 1 for the next digit for each 10 collected in the sum, and then finally reset which will be less than 10, and then finally we will move and we repeat this operation to get the value. So in the same way we can do the binary addition and subtraction. So the addition in binary is exactly the same as addition, with only one difference, which is that carry 1 is taken for the next digit for each 2 collected in the sum, and the reset which is less than 2 is left as a result of the addition of corresponding bits. So the addition is continued. The addition is continued for all bits including the sign bits, and in order to get correct answer, the number must be represented in n honor of bits. So what we need to do, the value of the negative result is represented in the 2's complement, and the actual values is the 2 complement of the result, and that is repeated. So this is something about the binary and octal number system and their addition and multiplication. What we do, we need to do the most important thing, that is the binary arithmetics, and the binary conversion process is most important was that if a number is given to us in the binary number system, how we can convert that particular number into hexadecimal number system. And similarly, if a number is given to us in hexadecimal number system, how we can convert that particular number into octal number system or some other number system. So we will be playing with such number system, and we will have some simple example. We already saw some example, and we will have more example as an assignment to solve the relevant problems, and to convert the values from one number system into other number system, so that we can play with this thing and understand the basic steps that are used for this conversion. So this is something about the number system. Thank you very much for now.